It's almost the end of the baseball season, and it's a race for the pennant. Only 2 teams have a chance of winning the pennant. The good guys and the bad guys. Both teams have 7 games left, but the good guys have a 3-game lead. What is the probability that the good guys will win? Let's find out. The first thing we need to do is find the probability of winning any given game for each team by dividing the number of wins by the total number of games. This gives us 0.62 for the good guys, and when we do the same process for the bad guys, we will get 0.6. When we subtract this number from 1, it'll give us the losing probability, which is 0.38 for the good guys and 0.4 for the bad guys. By using these numbers, we can find the probabilities of all wins and all losses easily. To find the probability of all wins, we need to multiply the winning probability 7 times itself, or to the 7th power. This would give us a probability of 3.5% for the good guys. And when we do the same process for the bad guys, it will give us 2.7%. To find the probability of all losses, you would just use the losing probability and multiply it by itself 7 times as well. This would give you 0.11% for the good guys and 0.16% for the bad guys for the probability that they would lose all 7 games. Great! Now we can just use this technique for the rest of the win-lose combinations, like if the good guys win 6 games and lose 1. Right?
No!
You see, there is only one way to win all games and to lose all games, but if you win 6 games and lose 1, there are many different ways, therefore there will be a different probability. To solve this problem, we can use something called combinatorics. There are 2 types of combinatorics: combinations and permutations. In combinations, order does not matter, whereas in permutations, order does matter. An easy way to explain combinatorics is by use of ice cream. If you wanted 3 scoops of ice cream in a bowl, the order in which you put the scoops wouldn't matter because the ice cream would just get all mixed up anyways. This is an example of a combination. However, in an ice cream cone, order does matter because you might want to eat one flavor before the other. Therefore, an ice cream cone would simulate a permutation in which order does matter. For example, if you were in an ice cream shop with 20 different flavors and you wanted to know how many different ways you could have ice cream in a 3-scoop bowl, you would go to your calculator, hit 20, then go to the math menu and select the probability menu, in which you would choose combinations because in a bowl, order does not matter. And then you would hit the number of flavors you wanted, 3, and then you would get 1,140 different flavors in a bowl. In cone, order does matter, so you would do the same thing, except under the probability menu, you would go to permutations and PR, in which order does matter, which would give you 6,840 different ways. To relate this back to the pennant problem, we would use combinations, as the order in which you win or lose the games doesn't matter. It's just the final score that matters. Therefore, we would use our newfound combinatorics knowledge and combine it with what we use to find the probability of all wins and all losses. For example, if we wanted to find the probability that the good guys would win 6 games and lose 1, we would do 7, go to the probability menu, select combinations, and then select 1 as they lost 1 game, and multiply this number by their winning probability to the power of the games that they won, and then multiply that by the losing probability to the power of the games that they lost. This would give us the probability that they won 6 games and lost 1, which is approximately 0.151. We could then do this for all the different win-loss combinations for both the good guys and the bad guys by using this process. The next step we need to do is use a probability outcomes chart, which you see on the screen, to determine the probability of a specific win-loss combinations for the good guys and the bad guys combined. We first labeled each cell for the probabilities of each team winning a specific amount of games and losing a specific amount of games. We could then multiply these together to find out the probability of them both happening at the same time. We then labeled each individual inside cell for if the good guys would win, the bad guys would win, or if it was a tie. The good guys are represented by blue. The tie is represented by orange, and the bad guys winning are represented by red. We then multiplied each individual probability for the good guys win-lose combinations and the bad guys win-lose combinations to find the probability of both occurring at the same time. If you were to add up all the cells, they should equal 1, or 100%. Therefore, we simply need to add up all the cells in which the good guys will win to find the probability that they will win the pennant. We can also use the same technique to determine the probability that the bad guys will win the pennant, or that the bad guys and the good guys will be in a tie. After we add up all the cells, we get a 1.727% that the bad guys will win the pennant, a 5.14% that the pennant will be a tie, and a 93.13% that the good guys will win. It seems that the good guys have a great chance of winning the pennant. Go good guys!